Now, what we know from calculus is, in calculus you deal with real-valued functions of a real variable. You define the derivative of this, but you also have real-valued functions of several variables, and here you define partial derivatives. Now here we are interested in defining derivatives of vector-valued functions of several variables. P and Q can take on any positive integer value. Now, the way we will proceed is we will actually take the notion of a derivative in the one-dimensional case. We will write the definition as we do it in calculus. But that will make no sense as it stands when P and Q are not necessarily 1, if they are larger than 1. But then we will try to write an equivalent form to the standard definition of the derivative of a real-valued function of a real variable at a point in calculus, such that it makes sense also whenever P and Q are any numbers. And then we will take that as our definition of a derivative. Okay? Well, once we do that, you know several properties from calculus and advanced calculus, well, how the partial derivatives are related to each other, well, and so on and so forth. Then we will discover all those calculus properties from our definition. So that'll take 1 week or so. I mean, not more than that. So it will be short. But for that, in order to simplify the exposition, let me introduce the notion of the limit of a function at a point in its domain or at a cluster point of its domain, which we use in calculus a lot. Now, let X rho, Y rho prime be metric spaces F on X to Y. Well, so this is 2.1 is basic notions, the definitions. Basic definitions, let me say. A function. Now, in calculus, suppose this is the domain of your function, and your function is something like this. But this is not in the domain. This is not in the domain either. But you can consider the limit of the value of this function as x tends to a, although a is not in the domain. But a is a cluster point of the domain. So here again, we'll define, okay, now let me write it like this. That directly, that will be shorter. A in X and let me take this on A to y, a function. Now assume that A in X, not necessarily in cap A, is a cluster point. Of A. And let me take L in Y. Now we say that limit of f of x as x tends to A is equal to L if. Now comes the standard definition. For every epsilon positive, there is some delta positive such that for all x, now in the delta ball with respect to rho about A, but now I will use this punctuation notation, the punctuated delta ball. This will be the delta ball about A taken out. And we'll refer to this as the punctuated delta ball about A with respect to rho. But also that should be in A. Well, now X is delta close to A, but not A, because f of A may not even be defined. A need not be a point in the domain. Then we'll have rho of, well, or let me write it in the ball notation as well. That is f of x, that will be in the epsilon ball about L in rho prime. F of x should be epsilon close to L according to rho prime. So this is just a standard definition in calculus, but just this time we have modified it to x rho y rho prime. Well, uniqueness of limits, well, that easily follows here. So we'll talk about L as the limit of f of x as x tends to A. Well, we will not have time, but how do we define if we take now f on R to R? Now, or let me again take it on A to R, where A is a non-empty subset of R. Now we can take A in A, but also a cluster point of A, because if I wish to define the calculus derivative of f at A has to be in the domain, but it also should be approachable via points in cap A, so a cluster point of this. Now, we define the limit as the limit of this as x tends to A. Now, x equals A will not belong to the domain of this function, but since it's a cluster point of cap A, well, we can consider this limit. If this limit exists, and if it's equal to A, then we say f prime of A is equal to L. But now, what if these are in RQ and these are in RP? P larger than 1, Q larger than 1. Well, if it's a vector-valued function of one real variable, this is a scalar, well then this still makes sense. But the crucial point is when P is larger than 1, then this will be dividing a Q vector by P vector, well, to which we have attached no sense, and it's very difficult to attach some reasonable sense to that. But now, by writing the formal equivalent of this, and then after a sequence of changes, all biconditionals, equivalences, we will write something equivalent to this when P and Q are both equal to 1. We are in the realm of functions, real-valued functions of a real variable. Well, we will reach an expression, a statement, which makes sense also when P and Q are any positive integers, and we'll take that, we'll adopt that as our definition, but we'll do it on Thursday. Now we had started to deal with differentiation. We wish to introduce the notion of a derivative of a function on Rp with values in Rq at some point A in its domain. Now, we start with a non-empty subset of Rp, f on A with values in Rq, a function. And then we take some point in A, but we do not wish that to be an isolated point, as we will be taking various limits as x tends to A. If it's an isolated point, then that does not make sense. So A in a cluster point of A. Now we wish to define the derivative of f at A. We know how that's defined when P and Q are equal to 1, A is a subset of R and has real values. Now let's reconsider that situation once more. Now case P equal to Q equal to 1. Well, let L be in R. Let us first remember the definition of the derivative of f at A being equal to L in calculus. Now, L is the derivative of f at A written as f prime at A equal to L if and only if the limit of f of x minus f of A divided by x minus A as x tends to A exists and is equal to L. Well, we have gone through the definition of the limit of a function. Now, this function is not defined at A, this quotient function, but as we consider the punctuated neighborhood and never consider what happens at x equals A, well, this is something well defined. But let me rewrite this in terms of the definition of the limit. This if and only if for every epsilon, there is some delta both positive, such that for all x which are delta close to A, but punctuated, delta close to A, but not equal to A, but also in A, then f of x minus f of A over x minus A minus L, the absolute value of that should be less than epsilon. As we wish to reformulate this condition in such a way that it also makes sense when we have a function on a subset of Rp with values in Rq, well, this is the absolute value, but the absolute value is nothing but the usual norm in R. So let me write this in the norm fashion. Now here, if it's on A with values in Rq, this will be P vector and division by P vector. We do not know what that means, and we do not know either what that can be given an appropriate meaning. Well, fx, fa, and L in this general case will be q vectors. So this will still make sense when p is 1. That is, this function is a function of one real variable, but it's vector valued, q vector valued. Well, then both of these will be q vectors. The norm will make sense. Well, as it is this division which actually leads to a problem, now let's multiply both sides of this by the norm of x minus a. Since we never consider x equal to a, the norm x minus a, that will be positive. If I multiply both sides by a positive number in an inequality, then what I obtain, that's equivalent to the former case. So this, if and only if, for all epsilon positive, there is some x delta positive, such that for all x in the punctuated delta ball about A intersection A will have, now this will become f of x minus f of A, then minus L times x minus A. Well, since this is still in the norm, the absolute value in here, that will occur like this, but that will be less than epsilon times the absolute value of x minus A, but let me write it in the norm form as well. Again, if we go back to the general case, these two norms actually will be different because this, given here in the general case, this will be in RQ, but this will be in RP. We do not know how to multiply P vectors with Q vectors. And well, these are in RQ. For this norm to make sense in that general case, this should be in RQ as well. If we can manage to give to this a meaning such that this turns out to be in RQ, then this will be Q vector, this will be the usual norm in RQ, but this will be P vector, and this will be the norm in RP. Okay, well, then let us go back to calculus and seek some help from there. Well, if in high school or in beginning calculus, you usually have a picture which accompanies the definition of a derivative. Well, let's take some such function. Let's take this point at A. Now, if f prime A exists, then it is geometrically nothing but the slope of this tangent line. And taking derivatives, that's somehow always associated with some kind of linearization. And that's here, well, if this is the derivative in here, and if you take some neighborhood away, this tangent line sometimes is taken as an approximation to the function itself. But now, first question, is the function whose graph is given by this is the function from R to R, whose graph is given by this straight line? Is that a linear map? Well, it's a line, so one might be tempted to think that it is linear, and well, linear, that means line-like. But let's first remember what the definition of a linear map is. Let V1, V2 be real vector spaces. F on V1 to V2, a function. Now we say that f is linear if and only if for any real numbers, alpha, beta, and any two vectors, x, y, in V1, one has f of alpha x plus beta y equal to alpha f of x plus beta f of y. This is the standard definition of a linear map from linear algebra. Now, having been reminded of this definition, let's get back to our question again. Is the function whose graph is this straight line, is that a linear map on R to R? R is a real vector space under its usual addition and multiplication. It's not, but let's make a further observation here. Let us take alpha equal to 0 and beta equal to 0. Well, this is for all alpha, beta. Then you have here f of 0 is 0 times f of x plus 0 times f of y. So this will be 0. So if f is a linear map on V1 onto V2 or into V2, it need not be onto, then the 0 vector of V1, that has to be mapped onto the 0 vector of V2. Well, here, both V1 and V2 in our case are the set of reals, the real vector space of reals. So this has to pass through the origin in order to represent a real line. Now, well, later on, we'll come back to this and generalize it to an arbitrary dimension. Well, this will be referred to as an affine function and not a linear function. But is there a linear function which is closely associated with this? Well, the derivative, that's the slope of this line. F prime A, that's slope of the tangent. So in fact, if it comes to the derivative, the property of this straight line that we are interested in is its slope. So let me keep its slope the same and have a parallel line to that which passes through the origin. Now this will be a linear map. T on R to R is linear. And what's the slope? Well, F prime A is equal to the slope of this. But the slope of this, that's nothing but T of 1. Well, T of 1, because the slope is this divided by this, if this is 1, you just get the value of the function at that point. Okay? Well, then, moreover, again, from calculus and from linear algebra, what we know is T on R to R is a linear map, or linear map, mapping, function, transformation. They all mean the same thing. There's no distinction between them. It's just something historical. Some kinds of functions, well, we are accustomed to refer to them as maps, to some as functions, to some as transformations, to some as operators, and so on. They all mean the same thing. Is a linear map if and only if there exists some L in R such that T of U is equal to L times U for some L in R. And in fact, this L, given a linear map, well, this talks of the existence, but this will be uniquely determined. And each such function, that's a linear map. So these functions for each L, they actually give the totality, the entirety of all linear maps from R to R. Well, then we can take that side discussion into here and write the following equivalent formulation of the above statement. Well, if and only if there is some linear map T on R to R. Now I will write this in parentheses with T of 1 equal to L. We can delete this, but let's keep it now. Such that for all epsilon positive, there is some delta positive, such that for all x in the punctuated delta ball about A intersection A, we have f of x minus f of A. Now this will be what? Well, if T1 is L, this function is Tu equal to Lu for all u, according to the observation over there. Thus, this becomes the image of x minus A under this linear map. T of, this now is not a multiplication, T is a function. This is T of x of a, and that's equal to L times x of a. So it's exactly this, less than epsilon times the norm of x minus a. But now, if I get back to the general situation, where A is a non-empty subset of some Rp with values in Rq, then this linear map, that will be replaced by some linear map on Rp with values in Rq. Okay? Well, and that will make this entire thing, if I have here Rp to Rq, forgetting about this condition will make full sense. Why? F of x, that belongs to Rq. The function is on cap A, which is a subset of Rp with values in Rq. This is in Rq, this is in Rq. T is on Rp to Rq, but x minus a, that's a member of Rp. T of x minus a, that's a member of Rq. And this is the norm in Rq of a Q vector. Here, x minus a, that's a member in Rp, and the norm over there, that's the P norm. That is the norm, the usual norm in Rp. So what we have done in here is, if we adopt this definition for the general case, then we will be considering this linear map, this object, which is a linear map on R to R, as the derivative of this function f at a, instead of this single real number. But this single real number entirely determines what this linear map is. And when this linear map is given, we can discover back what, in a unique way, what this single number is. Well, so far, unless we also decipher what TU, whether TU has some meaning when U is different than 1, some meaning in terms of the derivative, well, this will be something fancy. Well, you can represent something by a real number, well, but then instead of doing that, you invent a linear map which is determined by that uniquely, but, well, we do not, if we're only interested in T of 1, and if we're not interested in T of U, when U is different than 1, well, this would become not something which does not deserve merit, okay? So, although we have discovered what the definition of the derivative of a function of this general type at some a is, instead of making that formal and continuing with that, let us continue this analysis here and try to see roughly, which we will make precise afterwards, after we formalize this, what TU means when U is different than 1. Okay. For that, any questions so far? Okay. For that, we need, again, some notion from calculus, which is the directional derivative. In case you have a real valued map of several variables, several real variables, Well, then you have the notion of partial derivatives, but you also have the notion of a directional derivative. Let us first make the notion of a directional derivative. Well, we'll do that in the general case, and let us then see, coming back to here, how that is related to this TU. But for that, we need some further apparatus. Now let xy be two members of RP. Now we will define some line segments in RP. Define the line segment xy. This will be a subset of RP as lambda x plus 1 minus lambda y, such that lambda is in 0, 1. This is a very natural definition of this. Now, this as lambda x plus 1 minus lambda y, such that lambda is in the open interval 0, 1. Then xy, x out, y in, lambda x plus 1 minus lambda y. Now we want this to include x, thus lambda equal to 0. That should be in here, but we wish to exclude 1, so lambda equals 1, this becomes x, that should be out. Now, xy, similarly, that will be lambda x plus 1 minus lambda y, such that lambda this time excludes 0, but includes 1. Are these sets the same if I take p equal to 1 with the intervals we have defined in R in terms of the order structure? Almost, but not exactly. Why is that? If I take x in R, and if this is in the usual sense, in the previous sense, what does that mean? That means the set of all real numbers y, such that x is less than y and y is less than x. Is there some such y? No. This in the order structural sense. But from here, what's xx? Well, this only excludes 0 and 1. Well, for example, 1/2 is in here. Take 1/2, you'll have 1/2 x plus 1/2 x, that's x. This will be singleton x. In fact, this will be true for all x. And the coincidence with this will be only in this case. Okay? But it will be clear from the context what kind of interval we mean. So, well, we will make no notational distinction between these two. Okay, it will be clear. Now, when we wish to define the directional derivative, whatever sense we attach to that, well, we first have to have some direction. some object which defines the direction, and well, if the function is defined on a subset of R, well then on the subset of Rp, then U in Rp, a vector in Rp, that would be appropriate to define the direction. But now, suppose this is A, suppose this is some point in A, which is also a cluster point. But if the function is defined on here, and if I choose the direction like this, well, then I would be moving away from points belonging to the set, and at those points the function would not be defined. So we need to make a distinction between vectors which point into the set, which is the domain of the function, and those which do not. Now let's first formalize that. Now let A be a non-empty subset of Rp. Assume that A in A is a cluster point of A. Now, in fact, this will, okay, but let me keep this and let U be a vector in Rp. Now we say that U points into A, cap A, at A, if there is some positive real number delta such that the line segment from A to A plus delta U, that entirely stays within A. Here, no matter how small I choose delta, A and A plus delta U will be of this form, but that will not be entirely within the set. But however, here, well, I can choose delta small enough so that this line segment stays entirely within here. Now, moreover, if I take any interior point of A, which will also be a cluster point of A, what can you tell about a vector in Rp, U, pointing into A at this point? Can you say the set of all such vectors? Everything. Because you can have a delta ball about this. Well, let's take a delta half ball about this, because this site will be in the set, delta half ball. There will be a delta half ball about this. Well, and if you take any U, the line segments you will get will be like this, and they all will stay within the set, okay? Okay, now once we have this, we are now ready to define what the directional derivative of a function f on A, which is a non-empty subset of Rp with values in Rq, in the direction of U, the derivative of that at the point A in cap A, which is a cluster point of cap A, in the direction of U, which points into cap A, at A. Now let's write that definition. Now we need a non-empty subset A in Rp, a function on A with values in Rq, now we assume that A is a point of cap A, but as usual, we wish to approach this point A via other points in cap A, so we require that this is a cluster point of cap A. A in cap A is a cluster point of cap A, and we take some U in Rp, which points into A at A. Now, the directional derivative of f in the direction of u at A, in case that exists, from calculus, in the calculus sense of definition of a directional derivative, that will be a member of Rq. So also let me take L in Rq. So we have all the pieces. We can now start with the definition. We say that L is the directional derivative of f at A in the direction of u if, well, let me first write that in the limit form. We have formalized this. What do? We take actually, we start from A, then we take f plus tu, then minus f of A. So, well, actually we approach A along the vector u if t takes different values and goes to 0, but we divide that by t, and we let t tend to 0 if this is equal to L. But let me also spell out in detail what this means in terms of the definition of the limit of a function we have introduced. Or equivalently, for every epsilon positive, there is some delta positive such that whenever I take t, this is the variable which tends to 0, in the punctuated delta ball about 0, so well, t is never 0, so this expression is well defined for all t in here. Not necessarily so. Well, in the original case, I intersected that with the domain of the function. But here, the domain of this function as a function of t, that is not cap A. Okay? This should stay in cap A, but so I can write that in an alternative formulation. If A plus tu is in cap A, thus this t is in the domain of this function, this implies that 1 over t f of a plus tu minus f of a minus L, that is less than epsilon. So the conjunction of these means t is delta close to 0 and t is in the domain of this function. Okay? Okay. Now, one question. This actually differs slightly from the definition from the definition of a directional derivative which is given in calculus customarily. Well, for example, u equal to 0. Well, that's a vector. Does it have a direction? No. But is this defined at u equal to 0? Well, if u is equal to 0, this becomes f of a minus f of a divided by t, but that's 0. For all t different than 0, well, so its limit is 0. So this directional derivative is also defined when u is the 0 vector. Moreover, well, although we refer to that as the directional derivative, if you take u different than 0, well, u and 2u is the directional derivative in the direction of u and in the direction of 2u, the same in here. They have the same direction, they determine the same direction, but here this definition not only depends upon the direction of u, but it also depends upon what the norm of u is. Okay, so let me write down those. U is equal to 0. And well, here also, and right, let me introduce a notation so that will simplify what we'll be doing. Write L equal to f sub u of a. F sub u of a is 0. For all functions with these properties, and for all a satisfying the properties over there. And f sub u a, in general, depends not only on the direction of u, but also on its norm. So it's dependent upon the entirety, the entire information that u carries. Now let us, what were we interested in? Well, we said, well, let's check whether, okay, well, f prime a, that was a single real number. Well, instead of this, let's represent this by the linear map, by an entire map where, well, t of u is equal to f prime a times u. Okay? Yes?
What if the norm is finite?
Huh?
If the norm is finite, I mean...
The norm is finite. What?
I mean,
This is the usual norm.
Why does it depend?
Now, we'll see examples of that, but here, go back to here. Well, what you do in calculus, in order not to make it dependent upon you, here you take u of norm 1. You take u divided by norm of u. Okay? Now here, f of a plus tu and f of a plus 2tu minus f of a, well, depending upon what the function is, it will make a difference. And we'll see examples of that as well. We'll see that it, but here, let's just go, because we'll see examples of directional derivatives and it will be clear. But in general, f of a plus tu minus f of a and f of a plus 2tu minus f of a, well, they will be different, and it is very difficult to imagine when you divide that by t and take the limit, they will be equal. And what you do in calculus is, let me repeat, you take here, just as the representative of the direction, u with norm 1. Here we do not do that. Now, let's get back to this situation again. Now, I will not write, but let's assume we have this setup. That is, A is a subset of R. F is on A with values in R. Lowercase a is in cap A and is a cluster point of cap A. And assume that F prime A exists. Now take any u in R and let us consider the directional derivative of this real valued function of a real variable at A in the direction of u. Well, what shall we do? Well, we'll take the limit 1 over t f of a plus tu minus f of a as t tends to 0. Now, when u is equal to 0, f sub ua, that will be equal to 0. That we know. Here, assume that u is different than 0. Okay? We know what happens when u is equal to 0. But in that case, what I can do is I can divide this by u and multiply it by u as well. If this limit exists, then I can take u outside. It does not depend upon t. This will be the limit of 1 over tu f a plus tu minus f of a as t tends to 0. Now let me make a change of variable here. Let me write this r and this r. From calculus we know, and we will, as I said, the conclusion that we will obtain in here, we will prove that in full and formally for the general case. So this is sloppy. This is the calculus way of doing things. Well, then this is u times limit r tending to 0, 1 over r, f of a plus r minus f of a. But what's this? This is nothing but f prime a. Well, just take a plus r as x, f of x minus f of a, then r becomes x minus a, r tending to 0 and x tending to a, well, they're the same. So this is equal to u times f prime a. But here again, this is u times f prime a, since u is equal to 0 in this case. But the function which sends each u to f prime a times u, well, we decided here, the function whose graph is given by this, to take as the representative of the derivative in here. So at any u, this value is the directional derivative of f at a in the direction of u. And this f prime a itself, that is the derivative of f in the direction of 1, where 1 is the standard basis vector of R. Now, when we take us to Rp and consider the standard basis vectors there, that is, the ith standard basis vector is such that the ith component is 1 and the rest is 0, then the directional derivative of the function in question at a in the direction of e sub I, in case it exists, that will be the partial derivative of f with respect to the ith variable xi. Okay, so here, at least in this case, this function has a full meaning. At each u, tu, which is f prime a times u, well, that means the directional derivative of f at a in the direction of u, according to this definition, which is formal. Well, we'll give a break and we'll continue next hour by formalizing this definition, but we will first define the partial derivatives, since we have the definition of directional derivatives, and then we'll actually find the connection between partial derivatives and the derivative as we define it, but next hour.